Happy Friday. Welcome to TV Happy Math Hour, our weekly interactive math reviews for Math 1314 and 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link so that the chat so that you may connect to your session if you're here for 1324. Without further ado, I'll pass it on to the presenters so that we may begin.
Good afternoon, everyone, and thank you for joining us again for the Friday Happy Math Hour. I hope that if you're here, you probably haven't taken your final yet, but today is our last day of summer one. So again, I'm glad that you're here joining us to review. So we'll give a couple of seconds for those who are going to review for the Math 1324. Again, the link is on the chat. Just click on it so you can go into that special room and review for Math 1324. Excellent. So we're going to go ahead and get started then. So today, as I mentioned, we are reviewing for your final exam. If you are doing a summer one, today is your final. If you are having a 10-week, again, then you're super ahead of your class, and I guess you're getting a preview as far as everything that has been covered in your Math 1314 class. So without further ado, let's go ahead and get started. So let's go ahead and review intercepts and testing for symmetry. So let's have this equation, y is equal to minus 2x plus 1. And if I want to find the x and y intercepts, so for the x-intercepts, we set our y equal to 0, and for our y-intercepts, we set x equal to 0. So let's go ahead and do that. And when we do that, again, we replace y with 0, and we solve for x. And when we do that, we get x is equal to positive 1/2. Yes? So we go ahead and put that as an ordered pair when y is equal to 0, x is equal to 1/2. All right, to find the y-intercept, we set x equal to 0. So when we do that, we get y equals 1. All right, so then now we can review testing for symmetry. So to test for symmetry, we have, we can graph it. We know that this is a line, but when we're testing for symmetry, we want to check for the x-axis symmetry. We replace the y value with the negative, and if we still get the same equation, then it has that type of symmetry. So let's go ahead and do that. Let's replace the y with a negative y. And when we do that, we see that we get a different equation altogether. So this equation does not have x-axis symmetry. If we want to check for the y-axis symmetry, we replace x with negative x. And we do the same thing. We will go ahead and simplify. And on this one as well, we see that we get a different equation by changing the sign on the x. So then this equation also does not have y-axis symmetry. And to check for the origin, we swap both of the signs, both for the x and the y. So when we do that, when we replace the x and y with the negative, we end up with a different equation again. So this equation being a line, and pretty much all lines do not have any type of symmetry. So they don't have x-axis or y-axis or origin symmetry. But these are the ways to test for symmetry. Let's look at a circle now, right? The standard form of the equation of a circle with a given characteristics. Okay, so we know that the standard form of a circle is x minus h squared plus y minus k squared is equal to r squared, where again h and k is our center and r is referred to our radius. So what we need to do is we just plug in our values that are given. Our center is negative 4, 2. So that's our h and k. Our 2 is for the r. And then we just simplify. So when we simplify, we end up with x plus 4 squared plus y minus 2 squared is equal to 4. Okay. All right, let's look at this example. Write equations for the lines through the given point parallel and perpendicular to the given line. So for two lines to be parallel, they have to have the same slope, different y-intercepts. And for two lines to be perpendicular, that's a special case, right? They actually have to form a 90-degree angle between the two lines. So let's first find out what our slope is. So given this equation, let's convert it into slope-intercept form. And that way we can identify what our slope is. So when we do this, we see that, let's see here, what have we done? We see that our slope is 4, right? So to find the parallel, we're going to use our point slope formula given by y minus y1 is equal to m times x minus x1, where x1 and y1 are the points that we want the line to go through, which is 8, 1. So let's just replace those. What we know, when we replace our x and y, we know our m, which is our slope. We went ahead and replace these variables and simplify, right? So, and we also, by now you know that the computer wants the answer in slope-intercept form. So we go ahead and solve for y, and we get y is equal to 4x minus 31. And we know that this is a parallel line to the given equation because, again, they have the same slope. Now, to get the perpendicular slope, I always like to tell my students it's like the opposite of the slope. So, and the way I get that is, first I have this 4, I take the reciprocal of this 4, which would be 1 over 4, and then I change the sign, right? So the perpendicular slope is going to be a negative 1/4. Then again, I go ahead and do the same thing. I go ahead and replace everything that I know into the point slope formula. I'm going to distribute and simplify. And then at the end, I'm going to solve for y because, again, they want the answer in slope-intercept form. And my answer for the perpendicular equation is y equals negative 1/4 x plus 3. Okay. All right. Let's look at these other examples. Let's go ahead and look at combination of functions. So we have function f, which is 9x plus 1. And I have function g here, x squared minus 4. And they want me to add f plus g. So basically, I do a little substitution, right? F plus g just means that I'm adding function f with function g, and I replace them with what they are. Function f is 9x plus 1, which was in red. Function g is x squared minus 4, which is in blue. And then I just combine my like terms, and I get x squared plus 9x minus 3. So if I wanted to find f minus g, again, I do the same thing. I do the replacement, substitute the function f minus function g, combine my like terms, simplify, and I get negative x squared plus 9x plus 5. What about multiplication? What if I want to multiply these two functions? Well, again, fg of x is just multiplying function f with function g. So again, function f is in red, 9x plus 1. Function g is x squared minus 4. And I'm going to do FOIL to simplify this. Combine my like terms, and I get 9x cubed plus x squared minus 36x minus 4. What about the last one? Division of functions, right? So the syntax is f divided by g of x. Basically, what they want me to do is just divide function f with function g. And on this particular example, I can't simplify. There's nothing that I can factor out and cancel. So my final answer is just 9x plus 1 divided by x squared minus 4. All right, so in your homework, it always asks you what is the domain of the division of the two functions, and they asked us that because, again, we always can have a restriction on our domain if we are looking at a fraction problem function, right, or rational function. So here, if we don't see it, we set the denominator equal to 0. We find out, is there an x value that will give us 0 in this case? So when we do that, we find out that if x is equal to plus or minus 2, we're going to get 0 there. So Our domain in interval notation would be from -infinity to -2, union from -2 to 2, and union from 2 to infinity. Okay. All right. Now, to do a little complete review, we know that if we wanted to know if a graph is a function, we would do a vertical line test. But now that we're dealing with inverse functions, well, the opposite of a vertical line is a horizontal line. So if we want to find out if a function has an inverse, we perform this horizontal line test. And what the horizontal line test says that if every single y value is represented with one x value, then the graph has an inverse. Okay, so let's go ahead and determine whether the function has an inverse. So they gave us a little restriction here, right? We want only the values of x that are greater than or equal to 8. And if it does, then let's find the inverse. So this does have an inverse. And to find the inverse of a function, all we need to do is replace the x values with y's and the y values with x, and then you solve for x again. For y. And then once we've solved for y, we got to change that to the inverse notation, which is f to the exponent of -1. So when we do that, when we replace the x with y's, we get x is equal to the square root of y minus 8. Again, we do a little algebra to solve for y, and we end up with the inverse. The inverse of the square root of x minus 8 is x squared plus 8. All right, so let's look at another example where we're going to graph functions. So they ask to sketch the graph of the function by applying the leading coefficient test, finding the real zeros of the polynomial, plotting sufficient points, that means extra points, and then drawing a smooth curve, right, to connect all our values together. So first, let's apply the leading coefficient test. So the leading coefficient test says that if your leading coefficient is a positive value, okay, depending on the degree of the polynomial, the graph is going to be pointing up on both left and right. If the leading coefficient is a negative number, and again, our leading degree of our polynomial is an even number, then the graph is going to be pointing down on the left and right. And that's what we have here. We have a polynomial of degree 2, which is an even function. Our leading coefficient is a negative number. So the answer for this one is our graph is going to fall both on the left and on the right. Okay? And now, so we have a little extra here. We get to that. So these are the rules that I kind of went through right now. So again, for this particular one, this is an even function with a negative leading coefficient. So our graph falls right and left. All right. Now, if we wanted to find the zeros of this polynomial, again, we are dealing with a quadratic. We can try to factor it. We can try to use some of our properties of the quadratics, or we can use our quadratic equation. So on this particular one, I think the best way is just to factor it, and we can see that we can factor negative x squared plus 12x minus 32 with x minus 8 times x minus 4. So the values for x that could possibly give us zeros for this equation are x equals 8 and x equals 4. So these are values that make our graph cross the x-axis, yes? All right, so here we want to find some additional points. We want to find the y-intercept. Our y-intercept is y equals negative 32. This is where the graph crosses the y-axis. Okay? We can use our vertex formula to find the vertex of this parabola. And we know that is a parabola because, again, we are dealing with the quadratic equation because of the exponent of 2. And we see that our vertex is at 6, 4. So with all this information, we can somewhat easily, come up with our graph here. We have a parabola that is pointing down because of our leading coefficient test. We have our points, our x-intercepts, We can, on our graph, we don't go all the way down to -32, so we know that our graph is going to cross at that point. But again, this is a rough sketch of this equation. All right, now let's look at find the rational zeros of the polynomial function. So first, we can use the rational zero test to find all the possible zeros. Again, this is just a test. Just like when we were to go get tested for COVID, right? We can either get a positive or a negative result. We wanted a negative result, right, for COVID. But for this one, these are just possible values that possible zeros that this test can provide. So again, these are not the zeros, these are just the possible zeros. And the rational zero test says that you get the factors of the constant divided by the factors of the leading coefficient. Now, you don't worry about the signs. You don't worry if they're positive or negative, because we're going to be looking at both positive and negative. So we're just looking at the values of the constant and the value of the leading coefficient. So in this particular problem, our constant has a value of 9. Again, I don't care that it's a -9. And leading coefficient is a value of 1. And again, I don't care that it's a positive one, because I'm going to be looking at both positive and negative. So we have this ratio of values. So our possible rational zeros with using our rational zero test are -9, +9, -3, +3, -1, and +1. Well, what can we do with this information? Well, we can use synthetic division to test these values out to see if we can find a true zero. So let's go ahead and start with 1 using synthetic division. We got to make sure that we have the polynomial in descending order, and we have a placement value for all. So we do. We have a polynomial of degree 3, and we have a placement value for all, and it's already in descending order: 3, 2, 1, and the constant. So let's go ahead and do our synthetic division. We bring down the 1. We multiply 1 times 1. It's going to give us 1. 1 plus 1 is 2, and we do it again. 1 times 2 is 2. -9 plus 2 is a -7. That's supposed to be a -9. So again, this value is incorrect. It should be -16. But again, since we got a remainder, 1 is not a true zero. So let's go ahead and try -1. Let's do this again. -1 times 1 is -1. 1 minus 1 is 0. -1 times 0 is 0. -9 plus 0 is -9. -1 times a -9 is a +9. Again, that one was a -9. -9 plus +9 is 0. So we found one. X equals -1 is a zero of this polynomial. So that makes us very, very happy. And the reason why that makes us happy is because the quotient is a simplified polynomial. We can get the quotient, and our quotient is x squared minus 9. We lost the x here. So now that we have this, we can find the 2 remaining zeros that are missing, right? So we can add 9 on both sides, gives us x squared is equal to 9. Take the square root of both sides. So we know that x is equal to plus or minus 3. So this is a polynomial of degree 3, and we found our 3 zeros. We have -1, +3, and -3. So these are our 3 zeros. We can get the factors of these zeros. So it's just solving for zeros. So the first factor from x equals -1 is x plus 1, x plus 3, and x minus 3. Again, I plot these points, and we can use our leading coefficient test to find the behavior of our graph. Since this is an odd function, and our leading coefficient is positive, that means it's going to fall on the left, rise on the right. If we want it to be a little bit more exact, we want to pick a few more points to see what's happening between these points to get a more accurate graph, right? So oops. So I found these graphs, and then again, we would do a smooth curve, and this looks like a little wavy graph. Yes. All right. So let's look at this one. Use the given zeros to find all the zeros of the polynomial. So we have a function. It's another q function, x cubed minus 12x squared plus 52x minus 80. And they tell us that we have a 0 at 4 plus 2i. So we can use synthetic division also with imaginary numbers or complex um, numbers to simplify our polynomial. So let's go ahead and do that. Let's use synthetic division with this complex number that's in standard form, which is 4 plus 2i. We bring down the 1, multiply that times 4 plus 2i. That's going to give us 4 plus 2i. The way we add complex numbers is real with real, imaginary with imaginary. So we have a real number, which is negative 12. We're going to add it to the 4, which is going to give us negative 8. The negative 12 does not have an imaginary number, so that's 0 plus 2i, which gives us 2i. So let's go ahead and do that again. We're going to multiply 4 plus 2i with a negative 8 plus 2i. Again, that's a little FOIL. Let's go ahead and simplify this equation, put it in standard form by combining our like terms, and we get negative 36 minus 8i. Now we can add these two again. We add the real with real. 52 minus 36 gives us 16 minus 8i. Let's go ahead and do this last multiplication again. Remember, I squared is represented by a negative 1. And when we combine our like terms, we get 64 minus 16i squared, which is going to give us um, 64 plus 16, which is 80. And then negative 80 plus 80 is 0. So our quotient still has complex numbers in there. So what we can do is we can simplify it even further by doing it all over again. Let's go ahead and do synthetic division again with our quotient and simplify this, or perform our synthetic division. Again, we're bringing our 1, multiplying 4 minus 2i times 1. We get 4 minus 2i. In this one, we have reals and imaginaries to add. So negative 8 plus 4 is a negative 4. 2i minus 2i, that becomes 0. Let's go ahead and multiply this again. This one's an easy multiplication. We have negative 16 plus 8i, and when we add them, we get 0. Awesome. So our quotient now becomes an x minus 4. And it's easy to see that x is equal to 4. So we have our zeros. We have x equals 0, and then we have our x equals 4 plus 2i and the 4 minus 2. Okay. All right. Let's look at this rational function now. Again, rational functions are these functions that are fractions. We have 1 over x plus 3. So they're asking us to state the domain of the function. The domain of the function can be calculated by finding the restriction on the domain, or the restriction on the function. And on this rational function, since it's a fraction, we never want a 0 at the bottom. So we calculate that. Will x plus 3 ever become 0? And hopefully it's easy to see that if we have x equals a negative 3, that's going to give us 0 in the denominator, because negative 3 plus 3 is 0. So the domain for this function is all real numbers except for when x is equal to negative 3, which is that last one, right? So go ahead and continue. So now that we have our domain, we can find the x-intercepts. To find, again, this x-intercepts, we set y equals to 0. F of x is replacing y, so we go ahead just set this equation y over x plus 3 equal to 0. And then solve for x. Multiply both sides by x plus 3. We see that 0 is not equal to 1, so hence it's a false statement. So that means that we have no x-intercepts, and on the computer we would just state that does not exist. All right, what about our y-intercepts? Or to find our y-intercepts, we set x equal to 0. So when we do that, we get y is equal, we get y is equal to 1/3. So our y-intercept is 1/3, or as an ordered pair, when x was equal to 0, y is equal to the 1/3. Okay. All right, so to find the vertical and horizontal asymptotes, believe it or not, you actually already found the vertical asymptotes. The vertical asymptotes are those restrictions on our domain. So when we solved for the um, the domain, we actually found the vertical asymptote. And again, vertical asymptotes are these imaginary vertical lines that the graph cannot cross or touch. Okay, so again, when we found our domain for this one, we saw that we cannot use negative x equals -3, so hence that is our vertical asymptote. Our vertical asymptote is at x equals -3. Now, what about the horizontal asymptotes? Well, there's several cases for our horizontal asymptotes, and they all have to do with the degrees of both the numerator and denominator. So on our particular, let's go through the cases. So the first case is if the degree of the numerator is smaller than the degree of the denominator, we always have a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then we have a ratio, and that's y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. In our last case, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote, but keep in mind that when this happens, we have a slant asymptote. So let's look at our problem. We can look at our problem and we can convert that 1 into x to the 0, because anything to the 0 power would give us 1. So by doing that, we can see that 0 is smaller than 1 because the degree of the denominator is 1. So in our particular problem, it falls under this case. The degree of the numerator is smaller than the degree of the denominator. So hence we have a horizontal asymptote at y equals 0. Okay, so then we represent asymptote as dashed lines. We have our vertical asymptote here in red or pink as a dashed line at x equals -3. We have a horizontal asymptote represented here in blue as a dashed line at y equals 0. So let's put things together. We have our horizontal and vertical asymptotes. We have our x-intercepts that don't exist. We do have our y-intercept. We can plot additional points if we wanted to sketch the graph on this one. So by picking a few additional points, when x is equal to -2, we get y equals 1. When x is equal to +2, we get y equals to 1/5. If we pick some additional points, we can sort of come up with these points. And once we do that, we try to do a little smooth curve. Again, we're using the computer to generate that smooth curve. And you have this graphs. Again, these graphs they come very, very close to our asymptotes, but they don't cross or touch it. Okay? All right, so then again, this is our sketch, but there's always multiple choice on your computer for your WebAssign assignments. So what is the answer for this one that is represented on our multiple choice? And I would say that is our A, right? That A, if this is A, or I'm calling this one A, this would be our answer. Okay. All right, let's look at another example. Let's use the properties of logarithms to expand the expression as sum or differences and our constant multiples of the logarithm. So again, we have a log that has the same base, but the input is we have a division so that we can apply what's called our quotient rule. That when we have a log of the same base and we have items in there that are being divided, we can expand them by subtracting two logs. We have the log of the square root of x squared minus 9 minus the log of base 5 of 4. So it's the numerator minus the denominator. So now what we can see is we can write our square root as an exponent. And that will help us apply our power rule. So when we do this, we can represent the square root as a exponent of 1/2. And now we can apply our power rule. Says that when we have a log to an exponent, we apply our power rule and we just multiply that exponent to our log, which is going to give us 1/2 log of base 5 of x squared minus 9 minus log of base 5 of 4. But we're not done yet. This x squared minus 9, we can rewrite that. Okay, I see that as a difference of squares. So, or we can factor it. And x squared minus 9 is the same thing as x minus 3 times x plus 3. So now we have a log of base 5, and the input is two things that are being multiplied with each other. So now what can I do? What I can do is I apply my product rule. And my product rule says that when I have two elements that are being multiplied together with the same log, I add the two logs. So again, don't forget to carry the 1/2 that came from the exponent. So our final answer is 1/2 log of base 5 of x minus 3 plus 1/2 a log of base 5 of x plus 3 minus the log of base 5 of 4. Okay, so this is for expanding using our properties of logs. What about the opposite, condensing? Condensing means to put into a single log quantity. So let's go ahead and look at A really quick. Here at A, we have the log of x minus 6 log of y plus 7 log of z. They don't give us a base, but we know that when they don't do a subscript, we automatically assume that these are base 10. When they don't give us a base, we know that this is going to be a log of base 10. So hence, these three logs have the same base so that I can apply my properties. So let's first use our power rule that when we have a number being multiplied to the log, that is represented as an exponent. So we rewrite this as log of x minus the log of y to the 6 plus the log of z to the 7. Okay, we have no more values to multiply, or we have no more powers to apply. So now we just go through this graph from left to right. Okay, we have two logs that are being subtracted from each other, and they have the same base. So I'm going to, again, apply my quotient rule that this says that two logs that are being subtracted with the same base, I divide their input. So we have the log of x divided by y to the 6. This leaves me with now an addition. I can apply my product rule. Now when I have two logs that have the same base that are being added to each other, I can multiply the inputs. So we have log of base 10, again, x over y to the 6 times z to the 7. We can simplify it a little bit better so it can look a little nicer. Our final answer would be the log of x times z to the 7th divided by y to the 6th. Let's look at B. On B, again, we're using the natural logs. So we have, oh, sorry, I changed problems altogether. Let's just do A here for the natural logs, and we can move forward. So as you can see, the properties don't change whether we're using the science logs with a base or the natural logs. Again, these are called our natural logs. So let's look at this A. We have two logs that are identical. We have natural log of x minus natural log of x plus 6 is equal to 7. So we can condense the left side if we wanted to solve for this logarithmic. So we can do the division. We are applying our quotient rule. This is going to give us a natural log of x divided by x plus 6 is equal to 7. I think the easiest way or nicest way to solve these is to convert these into exponential form. So let's go ahead and do that. So the exponential form of this is given by, well, first let's change it to a log form so we can see better the exponential form, right? So the log of base e, the input is x over x plus 6 is equal to 7. So to change it to exponential form, it's the opposite, right? Logs and exponents are inverses of each other. So the log of the base has to be the same for both. So we have a log of base e, so that has to be also the base of my exponent, e. The input of the log becomes the output of the exponent, so is equal to x over x plus 6. And then the output of the log is the input of the exponent, so this e to the 7th. So we can first use our algebra to solve for x. We're going to multiply both sides by x plus 6. We're going to distribute our e to the 7th. Then we're going to move everything that has an x on one side, anything that just has a number to the right. Doesn't matter if you want to move it to the left or right. I like to have my variables on the left. So when I do that so I can go ahead and factor out the x, so I can isolate it. So I'm going to factor out the x now that they're both on the left side. And when I do that, I have x times e to the 7 minus 1 is equal to negative e to the 7 times 6. Solving for x, I just divide both sides by e to the 7 minus 1. And then now that I have this, I can just easily plug it into my calculator and solve for x. I get negative 6.005. Okay. Yvette, would you like to comment?
No.
Okay. Thank you. Let me go ahead and then continue. We always want to check our solution. Okay, once you have an answer, you always want to make sure that the solution fits. So if you see here, when we plug it in, negative 6.005, this does not give us the right answer. Negative 6 does not equal to the 7, so then this one has no solution. Okay. All right. We'll go ahead and skip B. It's more of the same. Again, we want you guys to review everything. Let's try to get, oh, actually, I have plenty of time. Like, we can do B. Never mind. Let's do B. So we have natural log of x plus 9 is equal to the natural log of x minus 6 minus the natural log of x plus 6. Again, we want to condense to help us out. We can apply our quotient rule again for the right side to condense that left side. So this gives us natural log of x minus 6 divided by x plus 6. Oh, and this one we can actually use our one-to-one property. Our one-to-one property says that when we have two logs that are equal to each other that have the same base, we just set our inputs equal to each other. So again, we are dealing with two logs that are the same. They're both natural logs. So for these two logs to be equal, x plus 9 has to be equal to x minus 6 divided by x plus 6. So again, we do the same thing. We multiply both sides by x plus 6. Go ahead and do the FOIL. Move all the terms to one side, combine our like terms. And we do that, we get x squared plus 14x plus 60. So again, we have a quadratic. We know how to find the x values of these. We can factor it. We can use our quadratic equation. On this particular one, let's use our quadratic equation for practice purposes. And I'm glad we did, because we could see that we have no solution. We're going to end up with imaginary numbers, even though at this point in time we know how to handle imaginary numbers. On this particular problem, we don't want to deal with those. So we know that this problem has a no solution. Okay. All right. Let's see. Let's look at another one. Let's solve the logarithmic equation. So we have log of base 9 of x minus the log of base 9 of x minus 8 is equal to a half. Again, let's condense the left side so we can solve for x. So we have log of base 9 of x divided by x minus 8 is equal to 1/2. Again, let's go ahead and change it to an exponential form. My log has a base 9, so my exponent also has to have a base 9. The output of the log is the input of the exponent, so that's 9 to the 1/2. The input of the log becomes the output of the exponent, which is equal to x over x minus 8. Again, let's do a little algebra. Multiply both sides by the x minus 8. Again, 9 to the 1/2, I know that's the square root of 9, which is going to give me plus or minus 3. Again, let me multiply both sides by x minus 8. I'm going to have two answers for the positive and negative. So for the positive 3, I get x equals 12. For the negative 3, I get x equals 6. So you always want to check these values to make sure that you get both a solution. So you see that when we use the x equals 12, we get the solution. But when we used, also both when we use 6, we get both a solution. So that, we get a negative value. So 6 is not a solution. So we only have one true solution, which is that x equals 12. Okay. Oh, and I am done. I went through these fairly quickly. I wanted to make sure that I covered a lot of material for you. Yvette, would you like to add something to our presentation today?
No, just I wish you well on your exams.
Excellent. So again, thank you guys for joining us. We do hope that you do very well. Hopefully these sessions have helped you out a lot. Thank you so much again. Please don't forget that if you haven't done so already, on the chat you had a link to get credit in case your instructor was giving you extra credit to attend these sessions. Again, good luck for all of you and enjoy your summers. Bye-bye.
Thank you everyone for your wonderful presentation. We do want to remind you about all our previously recorded sessions, which are available on the YouTube playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and another short survey to receive credit for attending. Before you all leave, I want to share the TVE sessions that we will have next Friday. Thank you all for coming in today. We hope you have a lovely weekend. If you have any questions, feel free to use the chat box or use your microphone. We hope to see you again everyone again soon.